This video is the first in a three-part series on uniform circular motion kinematics, and we're starting out in this video by defining average and instantaneous angular speed. Then we're going to look at how to write angle as a function of time when the angular speed is constant. So we've painted a spot on a rotating disk here, and we want to figure out how to define the speed of that spot in the angular sense. We allow the spot to trace out a sector during a time of delta t, and now we can label a change in angle for the spot, delta theta, where theta is measured in radians. Now the average angular speed is defined using the Greek letter omega with a bar over it for average. And that's the change in angle, delta theta, divided by how long it took, delta t. In other words, we're looking at the time rate of change in the angle. And again, what we're studying here is uniform circular motion kinematics, and that means omega is constant. That means our average angular velocity is just equal to the same number all the time. So we can just replace omega bar with omega, and I have a delta theta over delta t. Notice that the units of omega are going to be radians per second. Radians for the angle, seconds for time. And I prefer to write the units that way, but remember radians are technically unitless. So you could write it as just inverse seconds, 1 over seconds, or even seconds to the negative first power. I've definitely seen that in more than one physics book. So there's our formula for the angular speed when we have uniform circular motion. Now we can turn this equation around. So I could write delta theta, the change in angle, is equal to the angular speed omega multiplied by the amount of time. And this is really just the angular version of distance equals rate times time. Now it's common to take a starting angle of 0, and even more common to take a starting moment in time of 0. And this allows us to write our new formula in a simpler way. I can say that theta, as a function of time, provided I'm starting at theta equals 0, is equal to omega t, provided I'm starting at a time of 0. And this little equation gives us angle as a function of time for an object in uniform circular motion. And we're going to use this in a critical role when we derive the equations of motion for uniform circular motion in the third video. And I'll post a link to that at the top really quick. Finally, there are times where we want to apply calculus to expressing the instantaneous angular velocity. And this will be important when we study angular kinematics in a more general way. All I have to do to properly define the instantaneous angular velocity is take a small time limit of the average angular velocity. So I want the limit, as the time interval shrinks to 0, of delta theta over delta t. That's just d theta dt. In other words, the proper definition of our instantaneous angular velocity is going to be theta prime of t, where theta of t is the angle as a function of time. The next two videos in the series are linked at the left side of the screen. In the second video, linked at the top left, we're going to look at the relationship between linear and angular motion. Then in the third video, linked at the bottom left, we're going to derive the equations of motion for uniform circular motion, including the famous equation A equals v squared over r for the centripetal acceleration. Thanks for watching.